It is Wednesday, my dudes.
3, 2, 1. Oh shit. He's coming back on, isn't he?
So this is another tutorial video for KingsRockSim. I'm just putting this one out there because a feature was added just prior to the beta test. Coding for failure modes, rocket failure modes. So we'll just run the program as normal first. It doesn't matter what inputs you put in here. Eventually we'll get to the stage where it asks us whether we want to simulate the possibility of failure modes occurring. So we'll do yes for that. And now we have two options. You can either select a particular failure mode to simulate, so that failure mode will be forced to occur during the simulation. And this way you can see how a particular failure mode affects your simulation, or you can include a random factor into the simulation based on the likelihood of any given failure occurring. So we'll try the latter option first, and the failure modes that can be simulated are listed in the command window. There are exceptions, please read the descriptions. So if we just scroll back up, so the failure modes that can be implemented into the simulation are as such. The first one, unstable rocket instability. Now this one is, by the nature of the program, already implemented. If your rocket design is dynamically unstable, that will be visible when you run the simulation normally. So that isn't an additional form of failure mode that will be included here. The second is lawn dart. That's a type of recovery subsystem failure where the nose cone remains attached. That results in a ballistic flight. So imagine if you launched your rocket without a recovery system at all. You would simply have a ballistic flight. The third is separation. So any form of component separation that occurs comes under this umbrella of the separation failure mode. So because this is very difficult to predict, you don't know what parts of the rocket might separate and for what reasons, this is not accounted for in the simulation. So you cannot select 3 as an option. Number 4, motor CATO. If you don't know what CATO stands for, you can look it up. It's a type of motor failure, and this can occur at ignition or during firing of the motor, so really at any point during the motor burn. And it's simply various kinds of motor failure that can occur, all come under this one umbrella. So that can be accounted for in the simulation, and we do that by negating the thrust that would normally be produced at a time after a particular random moment is selected during the motor firing. So the program takes into account the total burn time and calculates a random moment at which the motor will fail during that time. And so thrust is zeroed for every time step hence after. Number 5 is referred to as core sample. It's another type of ballistic flight like the lawn dart mode, but the nose cone does eject whilst remaining attached to the rocket. So in this case the nose cone ejects, but for whatever reason your parachutes fail to deploy. So maybe they become tangled within the shock cords, for example. So we account for this by negating the effect the parachutes would have, but we increase slightly the reference area used in the drag calculations, because the nose cone, while attached, acts as a not very effective form of streamer. It adds a little bit more drag to the rocket overall. Number 6 is the motor is unrestrained. And what this means is if you haven't restrained the motor within the confines of your rocket, the motor may fire, but the rocket itself may not actually take off. So that leads to a failure similar to motor CATO. This is assumed that it can happen at any point during the firing. So your motor may seem secure initially at first and the rocket takes off, and then maybe the motor flies out from the front end of the rocket because it's not restrained within the body. So the same method to simulate that is used as it is for option number 4. Number 7 is rocket shred. Now this term simply means the rocket experiences complete destruction. So yes, maybe it explodes because of some kind of motor failure, but this could happen at any point during the flight, and there are various reasons that this could happen. So the way that it's been implemented in the simulation is we simply terminate at apogee, because we could calculate a random time during descent at which the motor may experience shred, but during ascent this would be difficult to do without knowing prior to calculating the trajectory up into ascent. It'd be difficult to know when it actually reaches apogee until that point. The final option is referred to as no-shoot. It's another type of recovery failure, but this last category accounts for non-ballistic trajectories where parachutes have not been deployed. But due to the difficulty in predicting a non-ballistic descent, so for example, perhaps the failure is such that the parachutes have come out, become tangled, but have affected the rocket trajectory in such a way that maybe it's flipped and started tumbling, that sort of movement would be very difficult to predict. So the simulation again will just simply terminate at apogee. The program then lists the percent probability of a given failure mode occurring. Now, based on historical data, a failure can occur in model and high power rocketry about 8.5% of the time. Now, within that 8.5% you have the 8 different categories of rocket failure, and each of those has a particular likelihood of occurring. For example, the rocket being unstable typically occurred in 19% of failures. Lawn darts occurred about 23% of the time, and so on and so forth. Now, since we earlier selected the second option for simulating failure modes, that is using randomization to determine 1, whether a failure mode will actually occur, and 2, should a failure mode occur, exactly what type of failure it would be. Now, this is based on the data you see in the command window now, all those numbers. So for this particular run, because the percent chance of a failure actually occurring is so small, in this particular run a failure did not occur, as it tells you in the command window. So we can continue running this simulation, but instead I will terminate the program execution at this point, so we can simply rerun the program and see how the former option plays out when you choose a specific failure mode to account for. So, as the program tells you at the very beginning, you can press the keys on the keyboard Control and C to terminate the program, and then you just hit the run button to start again. Now we'll skip this part, go straight to where it asks you about failure modes. We'll hit yes because we want to simulate the possibility of a failure occurring, but we will not use the latter method for randomizing failure mode occurrences. We'll use the former. We'll select a particular failure mode to simulate. Now, it will only list these failure modes the first time you run the program on your first run. So if you're doing multiple runs in order to compare results, maybe if you're keeping most of your inputs constant but changing 1 or 2 to see the effect they have, on subsequent runs, lists of information like this will not appear again. So, in terms of broad categories, for the types of failure mode we can simulate with this program, you have motor failures and recovery failures. So we'll try motor failure first. We'll choose number 4, motor CATO, and then we continue running the program as normal, import an engine file and so on. We'll skip down to the results. Now, when the flight simulation has concluded, it will tell you when the failure mode occurred and what type of failure it was. So it says failure number 4 occurred. So if we scroll back up to the list, you'll see number 4 was motor CATO, like we selected, and this was experienced at t equals 4s. That means a time of 4 seconds. So by random calculation, the program decided that the motor would experience that failure 4 seconds into flight. Now, for this particular engine file, the burn time was about 8.5 seconds, so that was about half the way into the burn. Now, if we look at the results of the simulation, we can see what effect that had. The apogee reached was less than 2 kilometers. That's about half of what we'd expect, which makes sense because we got roughly half as much thrust as we were expecting due to the motor failure. You also experience a lower maximum Mach number because it never quite reaches the sort of Mach 0.8, Mach 0.9 this particular rocket usually would. And then you can continue to view the rest of the results, but we'll cancel this and go back and have a look at recovery failures and the effect they have. So we'll skip through this section again. Yes to simulate the possibility of failure modes. No to use the latter method because we want to choose one this time. Those are listed. And now we'll go for a recovery failure. For example, we could go for number 8, no shoot, or we could go for lawn dart. Now lawn dart is the one with the ballistic flight. We'll go for that. So type 2 for that option based on the key provided, and continue entering the other usual inputs. Now, as you see here, the name I typed in for the engine file name was incorrect. I accidentally hit an extra button at the end. The pound sign, the American pound sign, or the hashtag symbol. Now, this will not break the program. I have accounted for this. A warning will pop up. In this case, the warning tells you that particular file cannot be located. That's simply because it doesn't exist. Now, for any other inputs, if you type something incorrectly, most likely it will give you a warning and tell you if it's incorrect. This is an example of where that occurs. So we'll retype that in correctly this time and continue running the simulation. We'll skip down to the results again, and this time failure mode number 2 was experienced at t equals 41.1 seconds. So 2 was lawn dart as we selected, and the failure itself occurred at 41.1 seconds into the flight. Now, given this particular failure mode's nature as a recovery failure, you can see based on the time that apogee was reached, 40.9 seconds, this is very close to the time at which the parachute would have been deployed. Hence why the failure mode was said to have occurred very close to that time. And the result of that failure mode occurring, as you can see, for the ground impact speed, it's very high, over 100 meters per second, where we're expecting somewhere between 5 to 10 meters per second if the recovery subsystem had succeeded in its job. And so that's an example of how a recovery failure can affect your simulation.